All right. Hello, everyone. Welcome back to AS 221. Today we are in Unit 8. We're going to be discussing the ILS and DME navigation. These navigation systems are typically used for landing. So we're going to begin discussing approaches in this unit. So we're talking about ILS and DME navigation. As an overview, we're going to talk about DME and the DME arc. We've talked a little bit about DME so far, distance measuring equipment, so you should be familiar with that. Then we're going to progress into the ILS system, the instrument landing system, and we'll talk about the localizer, the glide slope, and the marker beacons. We'll also touch on LDA as well as radar. So that is our overview. Our unit objective. The student will explain how a DME system works, understand the components of the instrument landing system, explain how a localizer and glide slope work, find ILS information using FAA publications, determine location on a localizer using marker beacons and DME, understand radar services available to pilots, understand how a transponder works, and determine when a transponder is required by the 14 CFRs. So that is our objective for today. The ACS and practical test standards. Task 2B, aircraft, flight instrument, and navigation equipment. The applicant demonstrates understanding of VOR, DME, ILS, marker beacon, receiver, and indicators, as well as RNAV, GPS, wide area augmentation systems, FMS, and autopilot. Here are the references for today. We're going to be out of the Instrument Flying Handbook. It's kind of your bread and butter for the course. Chapter 9, Navigation of Systems. The Instrument Procedure Handbook, also a great resource. Chapter 2, En route navigation. As well as the Cessna 172 NAV3 G1000 Pilot's Guide and the Cockpit Reference Guide for the G1000, as well as the ERAU interpretation of required G1000 knowledge. Again, these navigation systems are coming through our G1000, so that's why we will be referencing those from time to time. All right, let's review DME, distance measuring equipment. So DME operates in the ultra high frequency from 960 to 1215 megahertz. This is an active system, or what we call an interrogation reply. So the aircraft receiver is the interrogator, and we get a reply from the ground station. So we send a signal out and we get a signal back. That tells us how far away from the DME station we are. Again, DME stations are typically associated with a VOR, an NDB, or a localizer. And remember, very important, it measures slant range distance. So this slant range here. So you can see in this diagram, if we are horizontally 1 nautical mile from the station, and we are vertically 1 nautical mile above the ground, that would give us a slant range of about 1.4 nautical miles. So something you just have to remember, that it's measuring slant range. It's not measuring your horizontal distance over the ground to the station. It's measuring the line of sight distance. So what kind of stations give us DME that are charted, I should say? We have the VORTAC. Sorry, let me go back one. So again, the VORTAC, remember, it looks kind of like this triangle shape. Not sure how else to describe that. The VORTAC is a VOR that also provides some military services to the military. But for our purposes, remember that a VORTAC is always VOR with DME. So for our purposes, if you see a VORTAC, it's a VOR with DME. Then there's also VOR with DME. Remember, VOR with DME, we have the symbol, excuse me, we have the symbol for the VOR, and around that is a box. When you see that box around the VOR, that gives us VOR DME. Then there's also an NDB with a DME. And remember, we've talked a little bit about the NDB. That is a non-directional beacon. We on the low en route chart, we get this rings of circles with these dashed circles. That is an NDB. And if the NDB is associated with a DME, then it will also have this box kind of in it, I guess you could say. So there's an NDB with a DME. And remember, NDBs are very rare these days. They're really old technology, starting to get phased out. So they're kind of hard to find. And then next we have a localizer with a DME. The localizer, similar technology, you could say, to a VOR, but this is what's helping us land on a runway. So these are associated with runways, giving you direction to line up with the landing end of the runway. And then that's associated with DME, distance measuring equipment. So when you see a circle with a dot in the center and a box around it, that is a localizer with DME. All right, so we've talked about the DME, the distance measuring equipment. Let's move on to the instrument landing system, the ILS. This is how, remember, we're in instrument, so we are flying in the cloud. So navigation is very important because we are always going to be in the clouds. And we need to know where we are, where we're going, and eventually we need to find a runway. So we need a new navigation system that's specifically designed to help us land on that runway. So that's where the instrument landing system comes in, the ILS. You'll notice it's called a system because it's several navigation components that are all working together to give us horizontal and vertical guidance. So horizontal and vertical guidance. So things that an ILS is composed of, an instrument landing system, what is it composed of? So first, remember, ILS, we need horizontal guidance as well as vertical guidance. So for the horizontal guidance, the lateral guidance, we have a localizer. The localizer, as we'll look at in a minute, shoots off a radio signal in the horizontal direction. It shoots off two radio signals in the horizontal direction. This is what helps us horizontally or laterally align with the runway. So we are going to use the localizer to align with the runway, hopefully get us directly on centerline. Vertical guidance, again, as we come into land, we can't see, we don't know, what's happening outside of our airplane, so we need vertical guidance, or we need what's called glide slope. Glide slope works on very similar technology, very similar premise, but it's giving you that vertical guidance. So it's helping us find that perfect approach path, that vertical approach path that will lead us directly down into the runway. And then we have range information. So not only do we need horizontal and vertical guidance, but we also need to know how far away from the runway am I. And there's a couple of things that we can use to help us get range information. First is marker beacons. So there can be beacons along the approach path that help us identify where we are in respect to, or how far we are, I should say, in respect to the runway. Then there's just DME, which we've talked about, distance measuring equipment, as well as, in some cases, compass locator beacon. So these three components, and we're going to add four. We'll talk about the other one in just a second. But these three components are what navigate us to the runway. This is our instrument landing system. So again, the localizer giving us horizontal or lateral guidance from side to side, left to right. We have vertical guidance, our glide slope. This gives us up and down guidance. So we have left and right. This is giving us up and down guidance. Then we have range information, which gives us distance. And then finally, we have visual information. With visual information, eventually the idea is that you will break out of the clouds as you approach a runway using the instrument landing system. Eventually, we want to be able to see that runway. So we rely on approach lighting systems, so a series of lights that help us find the approach end of the runway, as well as the runway lights themselves. You've probably touched on this a little bit in your private pilot course. You might remember looking in the chart supplement and looking at the different lighting that a runway provides. And you might have noticed tons of acronyms, a lot of them confusing, but those were describing the different types of lighting systems we have. Okay, so here in this diagram, you can see kind of a visualization of what each of these things is providing. So you have the localizer transmitter. So you can see that's usually located at the far end of the runway. We have the glide slope transmitter. This is at the approach end of the runway, usually directly next to the PAPIs or VASIs. So whatever that visual glide slope indicators are, it's usually found directly next to that. And then you can see you have your middle marker and outer compass locator. So that is a broad overview of the instrument landing system. So let's talk about the localizer. Oops, sorry, I didn't mean to do that. Okay, so the localizer, now the slide might be a little confusing, so just bear with me for a second. A localizer, we're talking about localizer, is aligned with runway centerline. That's the idea. We use the localizer to align us on centerline. So you can see here in this diagram in the bottom right-hand corner, the transmitter itself is on the far end of the runway from where we are approaching. So if we are approaching from right to left, the localizer would be on the far end of the runway. And as you can see, it shoots off two signals. We have 150 hertz and 90 hertz. And your aircraft is picking up those two signals. So that's how it knows whether or not it's on centerline. If you get too far off to the right, it picks up more of the 150 hertz. Or if you get too far to the left, it picks up more of the 90 hertz. And when we're picking up both evenly, then we know we are perfectly on centerline. Okay, so that is a localizer. Again, if someone refers to a localizer, the big designator there is that it is aligned with centerline. Aligned with centerline. So just know if anyone ever references a localizer, that it is aligned with centerline. There is also what we call a localizer type directional aid. A localizer type directional aid, or LDA. LDA is the same technology. We're using the same premise, but an LDA, a localizer type directional aid, is not aligned with centerline. So in some cases, you have non-precision approaches that use a localizer to help you navigate to the runway, so to speak, but it's not perfectly aligned with the runway. So for various reasons, maybe just the design of the airport, for whatever reason, they have a localizer, but it does not align with the runway. But it must be, it's possible within 30 degrees. It has to be within 30 degrees of the runway. So what that means is typically you're going to have higher minimums. So it's not a precision approach, it would be a non-precision approach. And you would follow the localizer in, but it's just expected that once you break out of the clouds, you would then have be able to visually identify the runway, and then you would line up with the runway visually. So again, usually it's not that far off. It's only a few degrees off, at most 30. So when you break out of the clouds, you're not doing anything crazy, but you would have to then visually align with the runway. Range, a localizer in general, a range is about 18 nautical miles. So you can start picking it up 18 nautical miles out at an altitude of about 4,500 feet above the antenna. So full scale deflection is about 2.5 degrees, or on a VOR, it's about 10 degrees of deflection. Okay, so that is a localizer. Remember, a localizer is giving you the horizontal direction. So helping you align with the runway left to right. That is the localizer. Okay, so here are some examples of localizers and LDAs. So here on the left-hand side, we are looking at KPRC, our hometown airport, the ILS, or the localizer DME runway 21 left. So in this case, this is what the approach plate is gonna look like. We will discuss approach plates and how to read them later on in the course. But for right now, here are some examples. So you can see this kind of looks like a feather coming off of runway 21 left. So down here, you can see that is KPRC. And then you can even see the two sides of the localizer. So we have the 150 hertz side, the 90 hertz side. So you can see that they are shaded differently to help you identify. And this is what you would intercept, and this is what would guide you in to runway 21 left. This is giving you, again, horizontal guidance, or left to right guidance. Now, it says in the description, the name is the LOC. That stands for localizer, DME approach into runway 21 left. So when it says LOC, or localizer, we should know that to mean it is going to line me up precisely with the runway. So it's going to lead me right onto the runway center line. Now, if we look at KLGA here over on the right-hand side, you'll notice that we are working with an LDA-A. And it looks similar. They both look pretty similar. You can see we have this similar feather or arrow shape. You can see the 150 side, the 90 hertz side. You can see that they're shaded similarly. So they look very similar. But if we look at our airport down here, KLGA, you'll notice that the LDA does not perfectly align with the runway we are landing on. So I'm going to try to draw here. You can see the runway kind of comes off to the right of course here. So if you follow this localizer in, it would not perfectly align you with the runway. It would drop you off somewhere to the left of center line, and then it would be your job, once you have visual sight of that runway, is you would have to then visually align yourself with the runway. So that obviously happens if you break out of the clouds. You need to break out of the clouds for that to happen. Okay, so those are examples of the localizer and LDA. So remember, localizer, precision, it's going to get you exactly on center line with your runway. LDA, non-precision, it's going to get you close to the runway, but then you're going to have, once you break out of the clouds, you're going to have to do the extra little work of aligning yourself on center line. And then obviously that's something you will practice once you start flying instrument approaches. You'll do localizer approaches and LDA approaches. All right, let's talk about glide slope. Glide slope, again, this is still radio equipment. It's typically found about 750 feet to 1,250 feet from the approach end of the runway. So you can see down here we have the radio equipment, and you could say that's about 750 feet to 1250 away from the approach end of the runway. So it's very close. And it usually aligns with your PAPI or your aiming point. So it's guiding you down to where you would aim to land. So that's why it's usually directly next to the VASI or PAPI. And it works with a very similar system. Your aircraft is receiving two different radio signals. So if you're high, you're going to be receiving more of the 90 hertz, and if you're low, you're going to be receiving more of the 150 hertz. But if you're perfectly in between those, then you are on glide path. So again, glide slope is giving you vertical guidance, telling you, do you need to fly higher, or do you need to fly lower? So full scale deflection is about 0.7 degrees. So from this center line, the whole, you are trying to stay within a margin of 1.4 degrees, or 0.7 from each side of perfect glide path. So again, it is a radio frequency. It senses, your instrumentation senses whether you're too close to 90 or too close to 50, and it gives you that indication in the aircraft. Oh, and typically glide slope is giving you about 3 degrees of glide slope, what we'll call. So it's bringing you on a 3-degree glide path. Okay, so here are some examples. So we're still looking at KPRC. This is the ILS approach into KPRC. So you can see here in this satellite image, sorry, I had to get some water. We have our PAPI, and we have our glide slope transmitter. So you can see that the PAPI and the glide slope are both found in the same location. Now, what we're looking here over on the left-hand side, this is also associated with the approach plate. So if you look at an approach plate, this is a part of it. You would see a couple of different sections. They always give an overhead view and a side view. So you'll notice that this is giving us the path that we would fly vertically down to the runway, and it shows us, at a certain point at Humpty, about 10.5 DME from the runway, we should start receiving our glide slope indication, and that glide slope will guide us down to our runway. And you'll notice it tells us our glide slope should be about 3 degrees, and TCH stands for your touchdown height, how high you will be above the approach end of the runway on this glide slope. So once we pass over the threshold, we should be about 55 feet from the approach end so once you pass over the threshold of the runway, you should be about 55 feet high. Not a big deal when you're flying the Cessna, but that could be a bigger deal if you're flying a larger aircraft. So think about if we go to the extreme end, your A380, maybe the receiver for the glide slope is maybe on the nose, but there could be 20 or 30 feet height difference from the nose and where the landing gear are. So that's just something pilots of larger aircraft have to take into consideration, is how high above the approach end of the runway will I be if I follow glide slope. And again, this is something, this approach plate is something we're going to learn to read later in the course. So that is an example of glide slope. All right, now let's talk about the outer marker, or the marker beacons. The marker beacons in general are another tool that I would say will traditionally used to help us verify where we are in terms of distance. As we approach the runway, we want to have a couple of ways to verify, am I on course, and am I at the correct spot that I should be as I approach the runway. Because remember, there's a lot of stuff going on. There's a lot of things that you are managing during an approach. If we go back a slide and you look, our approach, we have a lot of altitudes, right? We start at 9,000 and we hit a certain DME at 16.4. Now we start descending. At a certain point, we should hit 7,900. That's where we should intercept glide slope. And so there's just a lot of things that we need to be paying attention to, distances, all that stuff, as we approach. So it's nice to have other indicators to help us relieve some of that, just that workload to help us understand where we are on the approach. That's where marker beacons come in. So the outer marker, the OM, or the locator outer marker, the LOM, helps us identify glide slope intercept. So this is an indicator that tells us this is where we should have intercepted our glide slope. So remember, the glide slope is just a radio frequency that's being shot off, two different radio frequencies shot off towards that approach. So eventually there is a checkpoint at which we should start to see our glide slope come alive. So that's why we have the outer marker. It's indicating this is where glide slope should be intercepted and where you are now responsible for flying glide slope. Then we can move to the middle marker, or the locator middle marker, the LMM. And this indicates our decision altitude. Our decision altitude is about 200 feet AGL off the ground, or what is also called the missed approach point. This is in instrument flying. This is a very important altitude, very important. Ideally, this altitude it's your decision, and what we call the missed approach point for a reason. It's where you should break out of the clouds, or at that point, you should have broken out of the clouds either previously or at that point. So remember, you're flying this instrument approach, you're in the clouds, you can't see anything. And at the middle marker, at this checkpoint, we should have visually identified the runway. And if you haven't, now you come to a very critical decision. And really, it shouldn't be a decision. If at this altitude you don't see the runway, you should execute a missed approach. So that means you're no longer attempting to land. Now you're going around to either try again or land at a different airport or a different runway under a different approach that allows you to make that landing. So you have to execute that missed approach. So this is a very important altitude. So when you hit this point, if you don't see the runway, you have to execute a missed approach. So you'll commonly hear it referred to as either the decision altitude or the missed approach point, where you need to make that decision if you're going to go around. Then last, we can have the inner marker, the IM. This is a further marker. This is even closer to the runway. And this is used for Cat 2 or Cat 3 approaches. This is the decision height for those aircrafts. Cat 2, Cat 3, these are high precision approaches. This is what like airliners are using. A lot of the times these approaches are completely automated. I believe with the Cat 3 approach, the aircraft essentially lands itself. So it's using autopilot all the way down to the ground to land on the runway. The pilots in the cockpit have some pretty advanced equipment. They have heads-up display that are giving them a virtual look at what the runway is doing, because the idea is that they want to be able to land essentially when the clouds go all the way to the ground, when there is clouds and a fog layer that's completely obscuring the runway. So if you've ever flown, airports in Seattle and Oregon and places where it gets really cloudy and really foggy, they're using Category 3 and 2 approaches. So it's pretty advanced stuff. So the inner marker is what those guys are using as their decision height. And equipment that substitutes when published precision radar for outer marking or middle marking. So sometimes we can use radar as opposed to these two pieces of equipment, or the DME for the outer marking. So the marker beacons, again, are a type of radio frequency. So these are stations that are now shooting a radio frequency straight up. And our aircraft has equipment that identifies those markers. So again, it's meant to take a little bit of the guesswork, a little bit of the mental work out of the approach. We just want to have these visual and audio clues that help us when we're making that approach. So for example, when I hit my outer marker, my final approach fix for non-precision approaches, in my cockpit, I should see a blue light. So I should see this blue light come on. So I know that I've hit that outer marker. If I hit the middle marker, I should see an amber light. And if I hit the inner marker, I should see a white light. These markers are then also associated with just Morse code. So each of them has a specific type of Morse code. The outer marker is all dashes. So you hear a dash, dash, dash. The middle marker is dot, dash, dot, dash, dot, dash. And then the inner marker is just dot, 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 dot. So that helps us using an audio or a tone helps us also identify these crucial checkpoints. So again, for us, that middle marker is kind of the most important one because that is our decision height. So that tells us this is where you should see the runway. When you hear that dot dash, or you see that amber light, you should see the runway. If you don't, you need to execute a missed approach. Okay, and then if obviously you're flying a more advanced aircraft, Category 2 or 3, then you would go all the way to the inner marker, and that is where your decision height is. So you can see here in a Category 1 profile, which is what we would be, you can see your final approach fix is associated with the outer marker. That's where you should intercept glide slope. And then at the middle marker, that's your missed approach point. So that's where you have to make the decision. Can I see the runway? If yes, you continue your landing. If no, then you execute a go around. So these outer markers, the outer marker, middle marker, and inner marker can be very important just as another aid to help us during an approach. They're not crucial. They're just kind of, and I don't want to say they're redundant, but we also should have distance information for each of these checkpoints. So using the DME, we should also know what is the distance of each of these crucial checkpoints. So that's something we should also be paying attention to. But these markers give us some extra buffer, you could say. An extra way, an extra aid to help us. So here's some examples of what you might see, how you would see these charted. In this case, for KSFO, ILS runway 28 right, this is a Category 2 and 3 approach. They only have a inner marker. So they only have that inner marker. So if you look at the approach as we come in, the inner marker is this very last thing before the runway. And again, that inner marker is the decision height for Category 2 and 3 approaches. So you can see it's specified with this kind of this little symbol here showing you that inner marker. And here we have an example of an LOM. So here we are at KYKM. This is an ILS approach into runway 27. And you can see here we have the Donnie, that's the name of the checkpoint, the LOM, or the initial approach fix. And there's only the one. There's no middle marker. There's only this one outer marker. Outer markers and middle markers are starting to become very rare. They're not very common anymore, mostly because GPS is taking over. There's no point in making these, because these are physical radio stations that have to be built off of the approach ends of the runway. So you can imagine, in cities, a lot of major cities that have big airports, if you follow that approach end of the runway out, you're going to end up over, someone's house where these markers should be. So that's why they're kind of rare to find. And especially with GPS, they're just starting to kind of be phased out. So we're using GPS in place of the outer marker and middle marker. So that's why you're just not going to find them as often. Okay, so let's watch a video. So we've talked about all of the different pieces. We've talked about the localizer, the glide slope, the marker beacons. So let's watch a quick video that shows them all happening together, all working together as one. So I don't believe there's much sound in this video, but you will hear the Morse code for each beacon. So let's watch. So as this aircraft comes in, I'm going to pause it real fast. You can see, I can't draw because this is in YouTube, but you can see in the top right, I guess you could say, we have our localizer and glide slope indicator. So you can see it's these two bars that kind of move around. The vertical one, the one that is up and down, is our localizer. It tells us whether we are to the left or to the right of course. And then the one that is horizontal tells us whether we are above or below glide slope. So this animation isn't the best because the actual airplane that you see seems to stay perfectly on glide slope and on localizer. But you're going to see the localizer jumping around a lot. So it just moves a ton. So try not to get too distracted by that. Eventually you'll see they get it perfect. But it just seems like there's a disagreement between what the plane is doing and what the receiver is doing. But let's watch. So there explains everything, tells you what's what. So you can see the aircraft is on approach. So at this point, we would just be going off of our altimeter, descending down to a designated altitude. And we're going to approach the outer marker. So you can see the blue lights, and we get the dashes, just all dashes. As we leave, that goes away, so we should be on glide slope now. We should have intercepted glide slope. And we're descending down to the runway, maintaining the localizer, maintaining glide slope. And you can see it's bouncing around. You can see the on the receiver there, those things are moving around. And as the pilot, you would be adjusting so they would stay centered. So you would stay on center line and on glide slope. Now we're going to hit the middle marker. So you can hear how it's different. You can see that amber light. And at this point, the pilot should have visually identified the runway. So that would have been the decision height. So based on the fact that he's continued, We can assume that he has visually seen the runway. Now he's going to pass over the inner marker. And touchdown. So that is how the localizer, the glide slope, and the marker beacons all work together to guide you down into the runway. So that is then the ILS in the works. Okay, and then we talked a little bit about how once we've broken out of the clouds, we still have to visually land on this runway. And we want to be able to clearly identify the runway. So we want as much help as possible as we're coming out of the clouds to be able to see that runway. So this is where the approach light systems, or the ALS, come into play. So there's a lot of them, a lot of acronyms. They get kind of confusing. And this is, again, if when you're in private pilot ground school, you probably learned to look through the chart supplement at the different runways, their different lengths, and the different types of lights that they have. So these are the different types of approach light systems that you might find on a runway. And the purpose is that as you approach, as we are beginning to break out of the clouds, ideally these lights would be so bright and so vivid that we would be able to see and identify the runway early, so that we would know, okay, I know I'm coming up to the runway. So that is the purpose of the approach light system. So we have the ALSF1, ALSF2, the SALSAR, the MALSAR, the REALS, the MALSF, and the ODALS. So there's lots of them. And you can see in this diagram, the only difference between them is just the way the lights are arranged, the colors, and how many lights there are. So you can see we kind of progress from very advanced with the ALSF 2 to the 1 to the SALSAR, MALSAR, the MALSF, and the ODALS. So the ALSF approach lighting system with flashers, or flashing lights, 1 and 2. So 2 is more intense. You can see kind of just based on the arrangement here, the ALSF2 is more intense than ALSF1. Then we have the SALSAR and the MALSAR. SALSAR stands for Simplified Short Approach Lighting System with Runway Alignment Indicator Lights. And the MALSAR stands for Medium Intensity Approach Lighting System with Runway Alignment Indicator Lights. So you can see those two here. And again, they're just getting less complicated. The lights are getting simpler. The REALS simply stand for Runway End Identifier Lights. Should have learned that one in private pilot, just telling us where the end of the runway is. Then we have the MALSF, which stands for Medium Intensity Approach Lighting System with Sequenced Flashing Lights. And then the ODALS, which simply stand for Omnidirectional Approach Lighting System. So a very simple lighting system. So again, these lighting systems are meant to help us. As we're coming out of the clouds, we want to quickly and visually identify the approach end of the runway. And so these lighting systems help us do that. So the ALS, Approach Lighting Systems. It's important to note, if you're going to land on a runway in instrument conditions, it's important to note what kind of lighting system it has. What should you be looking for as you come in to land? So my recommendation would be, if you come into an airport and you plan to do a specific approach, look at what kind of lighting system that runway has and maybe make a sketch of it, or do something to kind of remind yourself, what should I be looking for as I begin to break out of the clouds? Because that's going to be really key in helping you identify that runway. So for example, if you're coming to an airport and the runway is supposed to have ILS F2, and you begin your approach, but this is a very bright, vibrant light system, and if you can't see this once you hit that middle marker at that decision height, then I should probably do a misapproach if I can't even see the lights coming through the clouds. So it's good to know what lighting system does the runway I intend to land on have. All right, let's transition and talk about radar real fast. So radar stands for radio detection and ranging. Radar is very important. This is controlled airspace. Remember, this is ATC. This is how they are helping you navigate with radar. So it's a time interval between transmission and reception of signal. So the basics of a radar is you've probably seen that dish. It spins around. It shoots off a signal, a radio signal. That radio signal bounces off of things and it comes back. And when it comes back, it allows ATC to identify your range, so your distance, your azimuth, or which direction you're located in, as well as your elevation. So that is what radar is giving. So there's two types of radar. There's primary and secondary. Primary radar is a passive system. So it's just a signal that bounces off your airplane and it comes back. And that's the most traditional sense of the radar, is it just shows up as a blip on the radar screen. The secondary radar is what we call an active system. It interrogates the aircraft transponder. So it sends out a signal. Your transponder in your aircraft sends a signal back. So that way ATC can get even more information about your aircraft. So primary radar, there's good and bad. Primary radar offers separation of IFR traffic. So it helps ATC identify the different IFR aircraft and helps ATC keep separation between all those aircraft. They can provide traffic services such as sequencing and separation, used for surveillance radar and precision approach radar. So as you fly into class Bravo airspace, let's say, they're using, a lot of times they're going to use radar to vector you to the airport you need to go to. So they use radar as a form of navigation. They just tell you which direction to fly, what altitude, and they guide you along. The bad with radar is there's variation in size, shape, and the type of material can affect the target. So lots of things here. You could, depending on your airplane, the shape of your airplane can make the airplane look really small, or it can make the airplane look really big. Even things like a flock of birds could be confused as an aircraft if the flock of birds are in the right place at the right time and in the right shape, I guess you could say. It could be confused as an aircraft. There can be shadows or blind spots from high terrain or precipitation. This is same technology is used to see rain. This is how we identify rain on the radar. So if it's raining, that can block the radar signal, or terrain or other objects, such as a building, if it's in the line of sight, can block radar. So it has a lot of limitations. So primary radar is really good, but it also has some limitations. Secondary radar, again, this is what ATC uses to identify your transponder. So this is why they tell you to enter a transponder code so that they can identify you. It is an active system. The secondary radar will interrogate the transponder. So it sends a signal to the transponder and basically saying, hey, identify yourself. And the transponder replies with the code you have entered. So whether that's 1200 or the code that you've entered for whatever ATC has told you to enter, it will reply with that squawk code. And then even more so, some transponders will also give additional information. So here's what the radar screen would look like if you were air traffic control. You can see all the different aircraft flying around. It looks like here's an airport, so you have a lot of aircraft on approach here. So uses for radar, you can get radar vectoring. So that's where ATC will tell you a direction to fly. They will give you a magnetic direction, an altitude to fly, so they can navigate you places. They can provide traffic separation for safety. They can give you sequencing, weather, and traffic advisory. So there's lots of good uses for radar. So there's kind of two types of radar. The first of which is air route surveillance radar. So this is what they would use like if you're flying between airports. So the air route surveillance radar system, or ARSR. This is distributed over most of the United States. It's a long-range radar system. It's a large disk that rotates slowly and can extend or can detect aircraft up to 200 to 300 nautical miles away. So these are used by the different centers in the en route phase of your flight. So when you talk to like Albuquerque Center or Los Angeles Center, this is the type of radar they are using to give you guidance. So it's these big dome shapes. And the reason that dome is there is because inside is that spinning radar dish. So the dome just protects it. So that's air route surveillance radar. Again, this is what like the centers are using. Think big picture, en route phase of flight. Then there is airport surveillance radar, or ASR. This is smaller and faster rotating. This is what airports use to give you, vectoring or guidance when you're at an airport. So it moves faster, so they get more real-time information, so they can see what your aircraft is doing in real time. Again, ATC will assign a transponder code, so you become a specific aircraft that they see on their screen. So again, it uses that active system. It has radar that interrogates the transponder, and then the transponder replies with the squawk code. There's a couple different transponder types. The Mode A transponder can provide up to 4,096 possible squawk codes that ATC will have you enter. There's the Mode C transponder, which provides Mode A plus pressure altitude. So it tells ATC what your pressure altitude is. And then finally, Mode S provides everything Mode C has, plus additional aircraft registration info. So it gives like tail number and stuff like that. So these are the different transponder types. You want Mode S. Mode S is the best. It gives ATC the most information about your aircraft. And if ATC has the most information, then they can more accurately give you guidance. So those are the different types: Mode A, Mode C, and Mode S. You always want to know if an airport has radar services. So you would look this up in the airport chart supplement. And if you remember, when it talks about the different services you can talk to, if there is that tiny R next to the name of the or the call sign for that radio service, I should say. So an example, the New York approach control has radar because of that little R. New York departure control also has radar because of that little R. You'll see tower does not have its own radar. So that's how you would know who has radar available to them. And then you can read the limitations of radar in the airport remarks. So where do you need a transponder? Where must we always operate with a transponder? If we have one, it must always be turned on. If you remember, you need a Mode C transponder within what we call the Mode C veil, or 30 nautical miles around a Bravo airport. So if you look on a sectional A Bravo airport will have that ring. It's a magenta ring that says Mode C surrounding it. So that's how you know you'll need a transponder when operating within that airport. And then obviously within Bravo. So 30 nautical miles around Bravo, you need it. If you're actually within Bravo, you need it. If you're within and above Charlie, you need to have a transponder. If you're above 10,000 feet, you need to have a transponder, unless it's below 2,500 feet EGL, or if you're crossing an international border, then you need a transponder. So those are the times and places a transponder is required. Your transponder needs to be checked. So altimeter system and transponder need to work for pressure altitude reporting capability to be accurate. So this must be tested within 24 calendar months if you want to operate under IFR. So if you own an aircraft, this is something you need to make sure gets checked. And when you fly IFR, maybe at Embry-Riddle, you always want to make sure your altimeter and your transponder have been checked within the previous 24 calendar months. So very important. Always want to make sure your transponder has been checked and is up to date. All right, that concludes this lesson. So again, if you have any questions, feel free to contact me via Canvas, email, and if you want, I'm always available Monday through Friday for office hours. So if you want to set up an appointment with me, we can do a video chat and I can go over any information that you might be struggling with. So I know these video recordings can seem very one-directional, just me lecturing and you having to listen. But please know a part of my job is being available to you guys, which I am. During the weekdays, you are more than welcome to set up an appointment with me and we can set up a Zoom call or something, so that way we can go over any questions you might have. So please, at any point, if you're ever confused, don't hesitate to reach out. All right, I will see you guys next time.